Good morning, everyone. Myself Anu Kumari. Today I am going to prepare a audio recording for visually impaired students on the topic hard and soft acid and bases from Pradeep publication volume 3. The term acid and bases are routinely used in our daily life. Chemists have been classified substances as acids and bases since long time. Lavoisier noted that common element in all acids was oxygen. The word oxygen in Greek means acid former. However, Humphrey Davy showed later that all acids contain hydrogen. It was 1884. Arrhenius developed the theory of acids and bases known popular today as Arrhenius theory of acids and bases. According to Arrhenius, an acid is a substance which gives H positive ion in aqueous solution, and base is a substance which give hydroxy ions in aqueous solution. The strength of an acid or base is depend upon its capacity to provide H positive and OH negative ions respectively. The process of neutralization of an acid by a base can be represented by the reaction H positive plus OH negative in equilibrium with H2O. In 1923, J. N. Bronsted and T. M. Lowry independently proposed a new acid-base theory. According to their theory, an acid is a proton donor whereas base is a proton acceptor. The acid-base reaction, that is neutralization, is regarded as a proton transfer reaction. In 1923, G. N. Lewis gave another general definition of acid-base behavior in terms of electron pair donation and acceptance. However, this theory get recognized only in 1938. According to Lewis, an acid is a substance which can accept a pair of electrons, while the base is a substance which can donate a pair of electrons. In other words, an acid is an electron pair acceptor while the base is an electron pair donor. The earlier definition of acids and bases are solely based upon the observable properties such as taste, ability to dissolve substance insoluble in water, and their effect on vegetable dyes. The term acid was applied to the substances that have a sharp taste, turn blue litmus red, act with certain metals to liberate hydrogen gas, and have the ability to dissolve substances insoluble in water. On the other hand, the term base was applied to the substances that have a bitter taste, soapy feel, turns red litmus blue. However, taste and feeling chemicals are dangerous methods of determining whether the substance is an acid or a base. You should never even taste or touch solution of chemicals in laboratory. There are, however, other methods of recognizing acids and bases. For example, acids and bases change the color of certain dyes. One of the most common indicator is the vegetable dye obtained from lichen known as litmus. Aqueous solution of acids turn litmus red, whereas the aqueous solution of bases turn it blue. Thus, any substance which has an unshared pair of electrons can act as acid base, whereas the substance which has an empty orbital to accommodate a pair of electrons act as Lewis acid. In other words, substances capable of donating a pair of electrons are regarded as Lewis acid, or substances which are capable of accepting a pair of electrons are regarded as Lewis acid. Acid base or neutralization reaction may has be regarded as donor Lewis base, acceptor Lewis acid. Reaction of coordinate covalent bond formation reaction. The classical example of Lewis acid base reaction is that of between boron trifluoride, and ammonium. Using electron dot diagram, we can see the brown boron trifluoride is a Lewis acid and ammonium is a Lewis base. Ammonia with one lone pair and BF3 as Lewis acid react to give H3N with two lone pair and a coordinate bond with BF3. Lewis concept of acid and bases is a very commonly used because of its simplicity and the ease with formation of coordinate complexes can be explained. In brief, all the usual ligands can be regarded as Lewis acid, whereas all the metal ion can be regarded as Lewis acid. The degree of affinity of metal ion for ligands can be termed as Lewis acidity, and the tendency of ligands to combine with the metal ion can be regarded as Lewis basicity. Article 4.1 Hard and soft acids and bases. An acid-base reaction, according to Lewis' concept, involves the reaction between a donor acid and a acceptor B. As to form a complex as given below, A plus B with lone pair give A, B and B form coordinate bond with A. The formation of the stable complexes between the donor A and the acceptor B depend upon the nature of the species A and B involved. It has been known since long that certain ligands form more stable complexes with metal ions such as Ag positive, Ag2 positive, Pd2 positive, Pt2 positive. On the other hand, certain ligands form stable complexes with the metal ions such as Al plus 3, Co plus 3, Pt plus 4. Based upon the preferential bonding, the acids and bases have been classified into two groups, Class A and Class B, according to their preference. Class A includes alkali metals, alkali earth metals, lighter or more highly charged ions, for example, Ti plus 4, Cr plus 3, Al plus 3, Fe plus 3, Co plus 3, etc. Hydrogen ion and H positive ion. Class B metal includes higher transition metals of second and third transition series, for example, Cd plus 2, Hg plus 2, Pd plus 2, Pt plus 2. Higher transition metals in lower oxidation state, example, Ag plus, Hg2 2 plus, Cu plus. Low valent metal ions such as zero valent metal carbonyls. Depending upon the type of metal, ligand can be classified as class A and class B depending upon their preference. Class A ligands include molecules or ions with donor atom, nitrogen, carbon, fluorine, chlorine, etc. It is important to note that class A ligands prefer to form strong complexes with class A metals. Class B ligands include metal ions with donor atom, phosphorus, arsenic, sulfur, selenium, iodine, etc. Class B ligands prefer to form complexes with class B metal ligands. It was 1963. Pearson coined the term hard and soft acid and bases for class A and class B metal ions and ligands respectively. According, class A metal ions are referred to hard acid while the class B metal ions are called soft acid. Similarly, class C ligands are named as hard bases where the class B ligands are termed as soft bases. In summary, according to Pearson, class A acids and hard acids H positive, Li positive, Na positive, Be positive, Mg2 negative, Cr plus 3, Fe plus 3, etc. Class B Acids and soft bases. For example, Ag plus, Pd plus 2, ACu plus, Pt2 plus, etc. Class B. Acids and hard bases. H2O plus, NH3, F negative, ROH, etc. Class C. Acids are soft bases. R3P, R3AS, R3S, RESE, I negative, SCN negative, etc. Classification of acids and bases and as hard and soft. Pearson observed it is possible to correlate acid-bases interaction on the basis of hard and soft acid and bases. He observed that type A metal ions, that is acids, were small, compact and not very polarized. And these preferred ligands, that is base, that were also small and less polarizable. He called these acids and bases as hard. On the other hand, the type B metals, ions and the ligands they prefer appear to be larger in size and more polarizable. He described these acids and bases as soft. Pearson generalized the acid-base relationship as expressed that hard acids prefer hard bases and soft acids prefer soft bases. Classification of acids. In general, classification of some common hard acids and soft acids along with some borderline cases in given in table 4.1. Table 4.1 Classification of Lewis acids and as hard and soft acids. Hard acids include H positive, Li positive, Na positive, K positive, Be2 positive, Mg2 negative, Ca2 positive, Sr2 positive, Al3 positive, Sc3 positive, Ga3 positive, In3 positive, La3 positive, Cr3 positive, CO3 positive, Fe3 positive, As3 positive, Ce3 positive, Si4 positive, Ti4 negative, Zr4 negative, Th4 positive, Pu4 positive, Bf3, Bcl3, Alcl3, Alh3, Alch3 whole thrice, Cl plus 3, Cl plus 7, I5 negative, I7 positive, RCO positive, CO2, NC positive, HX. And the soft acids include Cu2 positive, Ag positive, Au positive, Tl positive, Hz positive, Pt2 positive, Cd2 positive, Pt2 positive, Hg2 positive, Pt4 positive, Ti3 positive, BH3, GaCl3, GaBr3, GaI3, INCl3. I positive, Br positive, HO positive, RO positive, I2, Br2, ICN, O, Cl, Br, I, N, RO free radical, RO2 free radical, metal free radical, CH2 and carbons. Borderline acids include Fe2 positive, CO2 positive, Ni2 positive, Cu2 positive, Zn2 positive, Sb3 positive, Bi3 positive, No positive, SO2, BCH3 whole thrice, GaH3, RH3 positive, IR3 positive, RU3 positive, R3C positive, SN2 positive, and Pb2 positive. As table 4.3 reveals that hard acids usually have the following characteristics. Hard acids are cations of smaller acids or lighter elements. Hard acids are cations of higher oxidation state, for example, Cl3 positive, Cl7 positive, I5 positive, I7 positive. Hard acids are molecules cations with lesser number of valence electrons. Fourth, hard acids hold the valence electrons tightly and consequently are not easily polarizable. In summary, hard acids bind strongly to protons. Hard acids are small sized, compact, and are not easily polarized. A close look to table 4.1 also reveals that soft acids possess the following characteristics. Soft acids are cations of the large size and higher element. Acids are cations of lower charge. Acids are molecules ions with larger number of valence electrons. Soft acids do not hold the valence electron tightly and are therefore easily polarizable. In summary, acids are large sized and easily polarizable ions molecules that bind strongly to highly polarizable ions and molecules. It is important to note that there is no sharp division between hard and soft acids. There are a number of Lewis acids that are neither too hard nor too soft acid. Such type of acids that are neither hard nor soft are called borderline acids, which are shown on extreme right of table 4.1. Borderline acids show Borderline acids have properties which are intermediate between that of hard acids and hard bases. In case of borderline acids, the properties such size, oxidation state, and polarizability of cation molecules are neither too low or nor too high. On the other hand, soft acid will show the opposite trend and the following order of preference of binding of donor atom ion with ion is observed. I2 negative is greater than Br negative, greater than chlorine, greater than fluorine negative. R2Te greater than R2Se greater than R2S greater than R2O. R2SB greater than R3AS greater than R3P greater than R3N. The above trend can be pictorially represented as Question 4.1. What type of interaction do you expect between a hard acid and a hard base? Answer. Since both hard acid and hard bases are not easily polarizable, their interactions are predominantly ionic. Question 4.2. What type of interaction do you expect between soft acid and soft bases? Answer. Since both soft acid and soft bases are usually polarizable, the interaction between them are predominantly covalent. Classification of bases. A general classification of some commonly used ligands, that is Lewis base, with hard acid soft bases along with borderline bases represented in table 4.2. Table 4.2 Classification of Lewis bases. Hard bases includes F negative, Cl negative, NH3, RNH2, N2H4, ROH, R2O, R2O double bond with oxygen, RO negative, H2O, OH negative, O2 2 negative, SO4 2 negative, PO4 3 negative, CH3CO negative, ClO4 negative, NO3 negative. Soft bases include H negative, R negative, I negative, C2O4 negative, C6H6, RSH, R2S. Borderline bases include Br negative, C5H5N, C6H5NH2, N2, N3 negative, NO2 negative, SO32 negative, SCORCN. A glance at the Table 4.2 reveals some of the important characteristics of hard bases. Hard bases bind strongly to proton. Hard bases contain donor atom of high electronegativity. The donor atom in the hard bases possesses low polarizability. The hard bases are not easily oxidized. Hard bases contain empty orbital of high energy. In summary, hard bases bind strongly to a proton. The donor atom in case of hard bases is the high electronegativity and of low polarizability. A further inspection of table 4.2 reveals that the following features are observed in case of soft bases. First, soft bases contain donor atom of low electronegativity. Second, soft bases contain donor atom of high polarizability. Third, soft bases get easily oxidized. Fourth, soft bases are associated with empty low-lying energy orbitals. In brief, soft bases contain less electronegative non-metal includes carbon, sulfur, phosphorus and iodine. The donor atom in such bases possess donor atom that are easily polarized. Just as there are borderline acids, there are borderline bases also. The properties of borderline bases are in between those of soft and hard bases. It is important to note that categories are not rigidly divided. For example, the halide ion form a series from the very hard fluoride ion through the hard borderline chloride ion to the borderline bromide ion and the soft iodide ion. The soft acid, also known as class B metal ions, are the group of metal ions which are in lower right portion of the metallic elements as shown in figure 4.1. Article 4.3 Pearson's hard soft acid and bases principle. Pearson proposed a simple rule of predicting the stability of coordination compounds formed between acids and bases. This rule is quite often named as HSAB principle. According to Pearson's HSAB principle, hard acids prefer to bind with hard bases while soft acids prefer to bind with soft bases. It is important to note that hardness and softness of acids and bases refer only to hard and soft interaction. It is why no mean related to the strength of the acids and bases. For example, both F negative and OH negative ions are hard bases with the basic strength of OH negative, that is equal to 10 to the raised power 13 times that of fluorine negative ion. In other words, hard acids will show the following order of preference of binding the donor atom with the group: F negative ion greater than Cl negative, greater than Br negative, greater than I negative. R2O greater than R2S, greater than R2Se, greater than R2Te. R3N greater than R3P, greater than R3S, greater than R3SB. Applications. Article 4.4 Applications of HSAB principle. Pearson's principle of HSAB has a number of applications in inorganic chemistry. Some of these are discussed below. Stability. First is stability of complexes. We have already noted that hardness and the softness of acids and bases are related only to hard and soft interaction. Hardness and softness of acids and bases has nothing to do with the inherent acid and basic strength of the acids and bases. For example, both OH negative and F negative ions are hard bases. Although OH negative ion is of stronger a base than F negative ion, in fact OH negative ion is 10 to the raised power 13th time more stronger a base than fluorine negative ion. However, in HSAB principle, both OH negative ion and fluorine negative ion are at par with each other. Parsons in 1963 explained the relative stability of coordination complexes on the basis of HSAB principle. Let us consider a general reaction between Lewis acid and Lewis bases.